And in this part, I'm going to describe the use of truth tables as a means to come up with a set of plausible guesses to interpret mass spectra data. So taking the raw data with the error bounds, namely a range of possible carbon compounds, come up with scenarios using a truth table to organize the scenarios and come up with an answer, or hopefully a set of answers. So just a quick review. We locate the highest M to Z cluster of peaks, assign an A, and assign the satellite peaks, namely A+1, A+2. We have to do a little bit of data manipulation if this peak that we're assigning to A is not 100% abundance. We have to scale it up. And then we have to do a little bit of thinking when we look at the prospective A peak, namely, is it odd or is it even? If it's even, then it is an intact molecule, and it must have, if it has nitrogen, an even number of nitrogens in that skeleton, that molecular skeleton. If it's odd, then it is a fragment, or it is a molecular ion with an odd number of nitrogens. These, again, are the isotopic abundances for the elements that we are considering in this course. 1.1% is the natural abundance of carbon-13. 0.4% is the natural abundance of nitrogen-15. 0.2% abundance is the natural abundance of the oxygen-18. Hydrogen is just treated as a single isotope. We use the information in the isotope lines to, in effect, count the number of atoms of a given type. And we come up with a range because we realize the limitations of the technique and the error involved. So as you can see in this particular example for the benzaldehyde, we have data that suggests a range of 6 to 8 carbons, and 1 to 3 oxygens. And the task is to come up with possible combinations of these empirical formula so that we can begin to look at other parts of the mass spectrum and refine our analysis. So we're going to come up with multiple guesses, multiple empirical formulas that satisfy at least the first set of lines in the mass spectrum. And then we're going to go down the line eventually to refine those guesses and hopefully rule out a few. And this will even work better if we have more spectroscopic information, such as infrared spectra and NMR spectra. So the truth table I'm referring to is organized as indicated. I have a column of guesses, numbered however many I want. And then I have across the rows, I have the number of carbon atoms, the number of nitrogen atoms, the number of oxygen atoms, the number of, the resultant AMU when I take those, and then the number of hydrogens I need to balance out the M to Z value in AMU. So in other words, finish off the molecule. SI refers to the saturation index, which you've encountered in organic chemistry. I'll review it in the next slide. And then yes or no, just convenience to see if that particular scenario is plausible. So I'll work through the benzaldehyde problem next. So starting with the benzaldehyde from the last lecture, or part of this lecture, the unknown I have postulated as having an A, being the molecular ion, having an M to Z of 106. And as the cat indicated, I have somewhere between 6 to 8 carbon atoms, 1 to 3 oxygen atoms. Saturation index formula is given below. And my first guess will just to see if there is a simple hydrocarbon that can give me this framework. And so I put in 8 carbons, 0 oxygen and nitrogen. I get 96 for the AMU. I need 106, so I add 10 hydrogens. And when I calculate the saturation index, it's 4. Here in the second guess, I've looked at another hydrocarbon, with this having only 7 carbons. And you'll see that when I work through it, again, 84 AMU for the 7 carbons, needing then 22 hydrogens to make the 106. So when I calculate the saturation index for this thing, I get a negative number, which clearly can't happen. So this is rejected immediately. The first guess actually is plausible. A hydrocarbon with 7 carbons in the skeleton clearly did not work because of the saturation index came out negative. So I need to add a heteroatom to the mix. As a first trial, guess number 3, I will add an oxygen to this 7 carbons. This gives me an AMU total mass of 100, and to reach the total mass of 106, I add 6 hydrogens. Saturation index is now 5, and that's an acceptable guess. My fourth and fifth guesses, I'll add another oxygen just for fun, but to get the masses down, I'll take away a carbon, so I'll have 6 carbons, 2 oxygens. That gives me a total AMU of 104. Requires 2 hydrogen to make out the balance to 106. Saturation index in this case is 6, and that's kind of looking funny. I don't really kind of like that. If you think about it, as a linear molecule, I would have to have 6 carbons lined up. At the end of the molecules, I would have to have a carbonyl group, like an aldehyde, and that would give me a CHO. And then all the carbons in between would have to be triple bonded to one another. Well, triple bonded in a single bond. So I have to bunch of triple and single bonds across the chain. Kind of implausible, so I'll reject that. The other heteroatom, namely nitrogen, I have to add in pairs. So I would have to add 2 nitrogens in this case because the A has an even value. So I know if I have nitrogens at all, they have to be an even number of them. So I go 6, 2, 0, gives me AMU of 100. I get 6 hydrogens required. Saturation index is 5. That's not so bad. That might actually work. So if we look at this from this standpoint, I have 3 plausible guesses. Guess 1, 3, and 5 are not so bad. Saturation index is high, but recognize that if I have a benzene ring, that gives me 4 units of saturation index. So right off the bat, I'm okay. And the last unit of saturation index could be the carbonyl oxygen. And as we know from the previous part 3, we know this happens to correspond to benzaldehyde. So there's your structure, the actual structure, and you see that it conforms to the truth table guess number 3. Let's look at a second example. I won't tell you what this is just yet. So we have the following mass spectrum data. We have M to Z 108 with 100% abundance, 109, 6.8, 110, 2.6, which looks kind of funny, and 111, which is 0.1. So the best estimate or best guess, so we say, for the A value or the A parent molecular ion is 108. And now if we assign the error 0.7 for the 109 peak, 0.3 for the 110 peak, we come up with a balance of 6 to 7 carbon atoms, more than 10 oxygen atoms based on the 0.2 per oxygen. Probably there's some chemistry going on, so this is going to be some funny business. We're going to have to work around this and figure out how best to attack it. And again, truth table is the way to go. So here's a truth table for that particular mass spectrum. I start off with the straight hydrocarbon system. So the maximum value of plausible carbons was 7. As a pure hydrocarbon, I wind up requiring 24 hydrogens and getting a saturation index of -4. Negative number's bad. Get rid of it. That gas is horrible. If I try that with 1 oxygen, 100 AMU, requires 8 hydrogens, saturation index of 4. That's not so bad. Okay, we'd accept that as a guess. If I work my way down, I try 6 carbons with 2 oxygens, 104, 4 hydrogens, saturation index of 5. Again, that's plausible. And then since it's an even valued molecular ion, or at least that's my prediction, I have to add nitrogens in pairs, so I add 2 nitrogens to this. 620, 100 requires 8 hydrogens, saturation index of 4, and that's plausible. So I have 3 good guesses and 3 empirical formulas that could possibly satisfy what I'm seeing in the mass spectrum. The actual molecule is benzoquinone, indicated here in the little cartoon. And you're probably wondering why there's an anomalous A+2. And the reason for that is that benzoquinone can be reduced to form hydroquinone, given here to the right. It adds 2 protons, and that accounts, so there's some beam chemistry going on. Protons are getting added to the beam, into the molecular ion, and coming out as an anomalous A+2 in this particular case. For curiosity's sake, if you look at the mass spectrum of hydroquinone, you get the following, with the molecular ion coming in at 110 and the 111 looking fairly normal, and a fairly normal A+2 at 112. Again, most of these rules I'm taking from standard textbooks on interpretation of mass spectra. These are the 2 that I have been using for the past 20 years or so. And just before we go, I want to say that you should be practicing mass spec interpretation by going to the SDBS database, which is where I'm getting all these examples. So this is a screenshot of a search, AIST spectral database. If you do SDBS database, you'll come up with this link, and it will take you to a sort of welcome disclaimer page where you agree to use the information on the website in good faith. And the search engine itself, you input the data in the language of your choice. Simply, you can do it by compound name, you can do it by molecular formula. The instructions are directly below the data entry port, or molecular weight, and you hit the search button, which is in the screen bottom to the left, and you'll come up with all the hits that correspond to the keywords that you use. From there, you click on the links and you will wind up getting the spectra and all the data corresponding to that organic molecule. So there'll be mass spec, NMR, infrared, other spectroscopies if they have been published. Sometimes you'll find electron magnetic resonance, but this is a useful source of information and practice problems for you to work through your own examples and learn how to do the interpretations that I've outlined in this particular lecture and all the 4 parts.